Okay, let's start on the Crescent Girls 2014 Physics Prelim paper. And let me apologize first. When I printed this out, I didn't know that I have actually printed out the marking scheme. So anyway, I will go through the marking scheme and then highlight to you some of the concepts used and break down the question into smaller parts so that you would understand it quickly. Okay, for section 1, question A is your typical kinematic question on speed time graph. So the concepts behind is gradient in speed time graph is actually your acceleration, and the area underneath the line is actually your distance. So actually part A, part B, part C is actually your typical calculation here. Part B get the gradient, part C get the area underneath, and you should be fine. Now for part D, when you need to describe the motion, most of the students should be able to tell me that because it is a straight line, and so therefore the acceleration is uniform, and because this is positive gradient, and so it is experiencing an acceleration, and the gradient here is negative, so therefore it is a deceleration. What most students find difficult to tell is the direction of motion, whether the ball is going down or going up. Okay, but for this question, it is actually quite simple. The context already tell you that it is dropping. Okay, because it is dropping, it started off as 0, and then the speed will begin to pick up because the ball is being pulled down by gravity. So in the first 3 seconds, it is quite obvious to tell that the ball is actually falling down, and it is important for you to highlight that point in your description for your part D. Okay, so you need to tell me in which direction is the ball moving, and then whether or not it is experiencing a constant acceleration or deceleration. Okay, so definitely because the abrupt change of speed here, this indicates that the ball has actually hit the ground, and the difference here, 29.4 changed to 19.6. It's actually because during the rebound, some of the kinetic energy has actually been lost to the environment in the form of heat energy and sound energy. So as you can see here, the speed is actually decreasing after the 3rd second, and that is because the ball is actually rebound and is going up. And because it is going up, but gravity is acting downwards, and so the speed must slow down. Okay, and therefore you need to tell me in the description in D that after the 3rd second, the ball is actually traveling up, but it is actually experiencing a deceleration. Now, if this question is carrying a bit more points, it is safer for you to calculate what is the acceleration value. That means you cannot simply assume that this is on Earth and the acceleration and deceleration is 10 meters per second square. Since they give you the values 0, 0 and this coordinate here 3,29.4, you can actually work out what is the gradient here. Okay, and it is good for you to indicate the value of this acceleration in your part D. Okay, but since the question is only carrying 2 marks, okay, it is optional. Okay, but it is always good that when you are doing your practice paper, have the habit of finding out that value. Okay, so for your part E is what I have said just now. Okay, during the rebound, so at this point here, the total energy in the ball is actually your half mv square, your 29.4 square. During the rebound, some of this KE is actually dissipated as heat energy and sound energy. So that's why there's a sudden drop in the speed here. So explain that in terms of energy. Okay, and you will be fine. Okay, question 2 is your pressure question. So down here, you notice that as long as you know, you need to take note of this statement here. Is very important. They want you to give the unit N Newton per cm square. This saves you time from converting this cm square into meter square. Okay, you can directly use the values here into your P equals to F over A formula. So in part 2, now even though this is 1 mark, I would suggest you put in a 1-line explanation on how you get this answer. So instead of just putting down this value, just put a bracket here liquid is incompressible, so therefore pressure is uniform everywhere in the liquid. So just have a one-line statement here. Okay, you never know during the O levels what is the marking standard. Okay, in your part 3, again, if you know that pressure is uniform everywhere, just manipulate with the P is equals to F over A formula, you will be able to find the force. This valve A, valve B could be quite difficult if you are not used to D&T, but for those who are good, you can intuitively tell what is going to happen just by looking at this diagram. Let me zoom in for you. Okay, so the question is asking you, when this lever is being lifted up, what will happen to valve A and valve B? So what happens is, when this thing is being lifted up, there will be a very small layer of vacuum between the piston and the liquid, and this small layer of vacuum is going to cause the liquid to get sucked up. And because valve A is closed initially, what happens is that the liquid that is going to be sucked up will come from piston Q. And when this thing, the liquid is being drawn into piston P, what happens is that valve B will get pulled in and then get shut. Okay, and because of that, valve B will definitely be closed. Now, when we look at the liquids around valve A, as this piston is being pulled up, the liquid around valve A will get drawn up. And what happens is that when the liquid gets drawn up, it will pull the valve A open along with it. So valve A will become open. So with this understanding, you can deduce that valve A will be open and valve B closed. Okay? Okay, for your question 3 is your typical heat transfer, heat capacity calculation. So for part A, please go and look at the textbook definition. Be very careful to specify it is for 1 kg because the word here is specific. So when you see the word specific, please bring in the mass, okay, of the body. Then after that, you are to calculate the heat required to melt and then raise the temperature from 0 to 63. So once you see that there is a state change, please remember to consider the latent heat of fusion. So your total heat required, you need to consider the heat required to cause the state change plus the heat required to raise the temperature. So just use your heat capacity formula and your latent heat formula, add them together, you will get the final value. Now part C, what you need to be careful is that when you are using the time, the 20 minutes here, you need to convert it into seconds first, and then you will get this 101 W. Okay, for part D, right, what you need to be very careful is which one is the actual value and which one is the calculated value. Now, this 20 minutes here is the actual time taken. That means you have conducted the experiment itself. Okay, and this value here, the energy required, is your calculated value. That means you do not know. It's not from the experiment. Okay, you just calculate it based on the ideal situation. And so this power value here is your ideal value. Now, if you are talking about the actual experiment to melt the ice, okay, the actual heat required will definitely be greater than 1:1 kilojoule. The reason is because you need to consider the heat loss or the efficiency of your oven and all that. So actually, what this calculated value is actually lower than your actual requirement. Okay, this value is lower than your actual requirement, meaning that in order to melt the ice in 20 minutes, you must have supplied more than this value. If you just supply this amount of energy, you will definitely require more time to melt and then bring the ice to 63 degrees Celsius. So meaning that the power rating of the oven must be greater than your calculated value here. Okay, and that is because in the actual situation, you must supply more energy than this 120,920 joules. Okay, and that is how you explain this. Now, before I forget, you notice here in your part B, okay, we round it up to 3SF in our final answer. But if you are going to use the value in your part B, okay, in your calculation here, you cannot use the 121 kilojoule. If not, you will have inaccuracy. Okay, you have to use, okay, the exact number that you have calculated in your part B. Okay, if not, you may not be able to get 101. You may be able to get 102 or something like that. Okay, so be very careful when you are bringing forward values in your calculation. Do not use the round up values. Okay, use the exact one. Okay, part 4 is your waveform. So determine the wavelength. You can either count the peak to peak. Okay, for me, I usually use the peak to peak distance in the graph because it is very easy to spot the position of the peak. Okay, and you can get the unit of the wavelength from here. So it is in meter. Sometimes it is in millimeter. Sometimes it's in other units. So please be very careful. Okay, look at the axis and then determine the unit used. Okay, describe the movement of B for one complete circle. So remember, your particle on the wave is actually moving up and down and not left and right. Okay, so you can either use up, down, or use lowest point, highest point, original position to describe the movement of B. Okay, movement of B. Okay, then after that, mark a point on the rope that has the same vertical speed as point A and move in the same direction as A and label this point C. Now, in order to find, okay, a point that is having the exact same speed, the same direction of motion, okay, this means that this point must be of at least one wavelength from A. Okay, so since A is here, one wavelength from it will be 0.4 meter from it. And so go and count 0.4 meter, you will be able to locate this point C, which is having the same vertical speed, the same direction, everything same. Okay, but it will be at least one wavelength away. Okay, for part D, the horizontal speed of the wave is this. Calculate the distance traveled. Okay, you know the speed. You were given the time. You can definitely find the distance. Just use your simple distance, speed, and time formula. Okay, so let's see. So for part 2 on the diagram above, draw the position of the wave for time equals to 0.10. Let's see how he deduced that. Did it tell you what is the period? No. Frequency. Okay, so what you need to do here is that you do not know at t equals to 0.1 how far has the wave moved. But what you know is that you know the speed of the wave is 2 meters per second. Okay, so what you can use is V equals to F lambda. Yeah, because you already know what is your wavelength. So from this, put in your values. You find out that your F is 2 over 0.4 and your F is actually 1 over T, right? So from this, you can work out that your period is 0.4 divided by 2, which is 0.2 seconds. So you know that the wave will move one complete wavelength in 0.2 seconds. So in 0.1 seconds, the wave is going to move half a wavelength, right? So what happens is this entire wave is going to shift half a wavelength at t equals to 0.1. So therefore, you will get, where's my highlighter? Therefore, what you need to do is that you take this original wave, you shift it half a wavelength down. Okay, so one wavelength is 0.4, right? So half a wavelength will be 0.2. That's why you can see that this point is shifted to here, and this point is shifted to here, right? And then this point is shifted to here. So what happened after t equals to 0.1? The whole wave is going to be shifted half a wavelength away. So that's how you get this answer. Okay? Okay, question 5 is actually a giveaway if you have studied your electric field. Okay, so what happens is that when you have a charged body here, you will induce the charges on the conductor and you will have field lines that is going this way. Remember, your field line will always flow out from your positive charge to your negative side. Okay, and be very careful when you draw the line. Although here the marking scheme, they only sketch it out. Please make sure that it is up and down, it must be symmetrical. Okay, when it exceeds the sphere, it must exit perpendicular to the surface. Can? Part B is your typical question. Remember to highlight that the charges is induced. Okay, that is the key word. The positive charge is being induced on the left hand side, and remember to state the statement unlike charge attract, and then indicate that there will be an attractive force and all that. Okay, and eventually you have to state the movement of the sphere. So you have to state that sphere B is going to move to the A. Okay, now for part C, instead of the wooden board, which is an insulator, you will now have a conductor. Okay, and this conductor is going to enable the movement of charges from B to A or A to B. So what will happen is that because A is being charged, so it will have an imbalanced number between negative charge and positive charge. Okay, so what happens is that the excess negative charge here will start to move from sphere A to sphere B. Okay, and because of this additional incoming flow of negative charge into sphere B is going to be negatively charged as well. So initially, let's say in B is going to have an equal number of positive and negative charge. But because the negative charge in A is flowing into B, now B also have an excess of negative charge. So overall, B will be negative charge as well. And because of that, A and B now having the same charge, the same, both of them are negatively charged. So like charge will repel. So both of them will now move away. Okay, you need to have that understanding. Okay, we'll continue with question 6. So when you are encountering this question, don't let the voltmeter and the ammeter confuse you. They are just measuring equipment. They are not part of the circuit. So you can just ignore them when you are considering whether this circuit is parallel connected or series connected. Okay, so if we treat the measuring equipment as invisible, you can see that AB and these two components are being connected in parallel. So meaning that the potential difference between them are the same. Okay, so since the potential difference between these 2 points is 6 volt, the potential difference between these 2 points will be 6 volt as well. So that's how you get this 6 volt. Okay, next you are to find out the ammeter reading when there's no light. So when there's no light, the resistance here is going to be 3.6 kilo ohm. And because these two guys here are being connected in parallel, the total resistance here will just be the 3.6 plus 1.2 kilo ohm. Okay, so you can simplify the circuit and you have down here 4800 ohm, and down here the resistance across A and B is a maximum of 600 ohm. So you can simplify the circuit this way. Okay, and you are asked to find this reading here. So what happened is that you can see that, okay, these two are being connected in parallel. So use your formula for calculating effective resistance for a parallel circuit. You can find that these two resistor, the combined resistance is your 533 ohm. So using this, you have further simplified your circuit into this. So this 6 volt, this is 533 ohm. So if you are asked to find the current flowing through here, it's very simple. Just use your V equals to IR formula, you will find the answer. Okay, next, you are to find the potential difference across the LDR while the circuit is placed under dim light. So let's erase these things. Okay, so when the circuit is in dim light, the resistance of the LDR will be changed to 1200 ohm. Okay, and conveniently for us, the fixed resistor is also having 1.2 kilo ohm. So what happened is, it's very simple. You know that the potential difference between these two components is 6 volt, and because they are having the same resistance, means that this potential difference is going to be shared equally to these two components. So just take your 6 volt, divide by 2, you will get 3 volt. Okay, because these two are of the same resistance. Yeah. Okay, so down here, state and explain what happened to the voltmeter reading when the slider X is shift towards point A. Okay, so what happened here is that you can imagine that between A and B, it is connected by a series of small tiny resistors connected in series. So when you shift the voltmeter towards A, what happened is that you are actually measuring so imagine now your point A is here, point B is here, and this has a series of tiny weeny resistors being connected. So what happened is that you are now connected a voltmeter like that. Okay, so as you are shifting towards A, then definitely your voltmeter reading will decrease because you are measuring less and less potential difference or less and less resistors. So that's why when you are sliding the slider towards A, the resistance across A and X is going to decrease because there will be lesser and lesser number of tiny weeny resistors across the wire, and because of that, your potential difference, the voltmeter reading is going to drop. Okay. Okay, question 7. Question 7, be very careful. You have to use your right hand grip rule to determine which side is your North Pole. So for those who are still not really sure how to determine that, so first of all, find out which is your positive, which is your negative. So current is flowing this way. So can you see this way? Okay, for those who are not very good, this pen represents the core G. Okay, the finger represents how the current flows. So you can see the current is flowing and then it's wrapping from the top. So it's wrapping this way instead of this way. This way is behind, right? This way is in front, right? And as you can see, the wire is in front of the core. So in front of the core. So now use your right hand, grip it, and use your thumb. So your thumb is pointing to the left. So your North Pole is on your left. So this is how they determine the North Pole here. Okay, so for your compass needle, okay, in my class I always teach you compass needle follow the magnetic field line. So if you know the North Pole is here, draw your magnetic field line. So just draw it out. Okay, ignore the compass, don't need to consider it. So your magnetic field line will always flow from your south, from your north to your south, And then down here you will have the butterfly wing. Down here you will have butterfly wing also. So it will go this way, this one will go this way. Yeah. So if you put your compass needle here, your compass needle is going to follow your magnetic field line. So ignore this diagram here. This diagram is when your switch S is not switched on. When your switch S is not switched on, the compass point here. But that one is won't affect us. So just follow this. You will see that, oh, okay, if you put your compass here, your compass needle is going to follow the magnetic field line. So it's going to point towards the left. Okay, so down here, that's what happened. Turn so that its north pole face the coil. Okay, so basically the needle will turn left. Okay, if the paper core G is replaced with a piece of metal, a piece of steel, state and explain what happened to the compass needle when the switch is closed and open after some time. Now you need to pay attention is that steel is a hard magnetic material, and a hard magnetic material means that it's going to retain the magnetic property even when this switch is being switched off. Okay, so when you're explaining, first address how will the compass needle point when the switch is being opened after some time. So first state that when the switch is being closed, the compass initially was this way, pointing to the right. When the switch is on, it will turn this way because it will follow the magnetic field line. So says that when the switch is closed, the compass will quickly turn to face the coil. And when the switch is open, normally when you are having the paper core, this thing is going to return because it's no longer being influenced by the magnetic field from the coil, because you have switched off the circuit, right? But this time when you have the steel, okay, so you switch on, it will turn this way. Okay, and because you have a steel core and the steel is a hard magnetic material, it's going to retain, okay, the magnetic property. So even when the switch is now off, okay, the needle will not return to its original position. It will continue pointing towards the steel core. Okay, so that's why at the last statement, please state that the steel is a hard magnetic material, is going to retain its magnetism, and the compass needle will not go back to its original position. Okay, the last part, when the battery is now switched to AC supply. So what the AC supply does is that it will flip its polarity. Okay, and now the steel bar is being removed. So describe what you will observe about the compass. Now, be very careful whenever the question tells you a value. This value, okay, you have to take into consideration this value, okay, when you're explaining what is going to happen. So this 5 Hz is going to tell you that within 1 second, the polarity of the power supply is going to switch 5 times. So you have to show to the marker that you have this understanding, okay, of the parameter that is being thrown to you. Okay, so what will happen is that, use your right hand grip rule. What happens is that your north pole is going to flip 1 second, 5 times, like that. So you have to write it in words. And you have to write it from the perspective of the compass, because the question asks you what you would observe about the compass. So when the magnetic field start flipping like that, your compass needle will also start flipping. So you have to say that, oh, okay, the north of the compass needle will alternatively face the coil and then face away from the coil. And then you have to bring in your understanding, okay, from this 5 Hz. You have to say that this happens 5 times every second. Okay, and you will get the full mark. Okay? Okay, part B is your database question. Okay, some of the things you need to take note, okay, is this thing. Okay, the weight of the valve. You have to use this data later in the thing. And you also need to take note of this. It's going to melt. And then you have to take note of data like this. Okay, you switch on for how long? So your part A is your standard kinetic model. Okay, how the pressure cooker increase? You have to state that okay, the volume is now being fixed. Okay, and the temperature is increasing, and so the atom molecule gains heat energy, and then after that it's going to move faster, and because it moves faster, collision with a larger force, higher frequency of collision, and so that the average force acting on the wall will increase, and then P equals to F over A, da 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 da. Okay, refer to your book if you are not really sure. Explain why your heater is placed at the bottom of the cooker. So this one is to test you whether you can explain your convection current clearly. So remember to state that it is the air that is expanding and resulting in a less dense situation. Okay, don't say that it is the air particle that expands. Air particle doesn't expand, it's the air itself. Okay, then after that you have to determine the pressure and hence the temperature in the cooker that will cause the weighted valve to open. So when you are looking at the valve, okay, the valve has a certain weight and a certain area. So what happens is that in order to open your valve, so let's say this is the valve, okay, this is outside of the pot, this is inside of the pot. Okay, so you have pressure from the inside and the pressure from the outside. Okay, the pressure from the outside, okay, will include the weight of the valve plus the opening, right? So the weight will cause a certain pressure on the outside, and plus the atmospherical pressure, okay, that is pressing onto your valve. So when you want to calculate the pressure outside, okay, please remember you have to take into account, so this first statement, the P equals to F over, the P equals to F over A, this one is the pressure from the weight of the valve. You need to add in the atmospherical pressure, okay, and if you sum these two up, you will get the total pressure that is on the outside. So in order for the valve to open, the inner pressure must be at least equal to the outer pressure. Okay, so once you get this 210 kPa, you can look here. Okay, 210 kPa, okay, it corresponds to 128 degrees C. So you get the temperature. Okay, okay, down here, when you are looking at when is the cooker cooking at the most efficient, the highest efficiency, basically, how do you define efficiency? Efficient, you say that the cooker is very efficient if it can bring the temperature up in a very short time, right? So you have to look at your table and find out that between which time did the temperature rise the most. Okay. Okay, then after that, suggest a possible reason for the change in the pressure at 300 seconds. So if you look at your table, you notice that at the 300 second, actually there's a drastic drop in your pressure. Okay, and actually you got a hint here. The alloy will melt when the temperature gets too high. And if you look at the temperature here, you can see that it is actually quite high already. It's 158 degrees C, and then suddenly it drops. So what possible suggestion here is that the alloy must have melted, and therefore the hot air that's inside the pressure cooker got released, and suddenly you see that the pressure actually dropped to almost the initial pressure reading. Okay, so that's one possible reason. Okay, finally, question 9. Okay, question 9 is your standard moment question. So at the beginning, you were told the bucket is steady, so just make sure you have the clockwise moment equal to an anti-clockwise moment. Do a bit of your algebra manipulation, you should be able to get the first answer. Second answer, you have to find the force acting at P. So you can see that the force acting at H is downward. The bucket here is also downward. So meaning that the force that is hidden here must be upward. And this force, because the whole system is steady, this upward force is equals to the combined value of the downward force. So that's why you have this. Okay? Bucket is lifted here, just use your MGH, it's alright. To find the power, you know the time, so you can calculate it, no issue, very simple question. Then you are asked for a reason why the power must be greater, and that is because in your whole calculation you have assumed that there's no energy loss. But in actual fact, as long as you have surfaces rubbing against another surfaces, you will have energy loss due to heat energy, due to sound energy. So just state that, you should get your 1 mark. Okay? Part D is your common sense question. You have to be able to tell that the purpose of this device is to reduce the amount of force required to lift the load, right? So therefore, you need to have a longer lever, okay? Because your moment is equals to F times D. So if your D is longer, it means that your F can be smaller, and with that smaller F, you can still produce the required moment to lift your load, okay? Okay, question 10 is another straightforward question on DC motor. A, I'm not going to talk about it. B, okay, for B, right, please remember this is motor, so please use your left hand rule. Okay, you are asked to find out the direction of AB. So positive is here, the current will flow here, then after that it's going to flow up. Okay, so FBI. B stands for magnetic field. So I, so your middle finger, you have to point up. Okay, point up. Then this finger is your magnetic field, is going to the right, so definitely your force is going down into the paper, down. So that's why you got the downward. Explain why the coil turn. Now, if I am the marker, I will not accept the explanation just by stating that, oh, it's because of Fleming's left hand rule. No. Okay? Please go and explain why does it move. Okay, you have to write down that when there's a current flowing through, okay, the wire in the coil ABCD, this current is going to generate a magnetic field around the wire. Okay, and because of this magnetic field is going to interact with the magnetic field in between the magnetic north pole and the magnetic south pole. So this interaction of magnetic field, okay, is going to cause an upward force on CD and a downward force on the side AB, and hence the coil start turning. Okay, what I'm looking for is that you have to highlight to me that when the current is being when the circuit is being switched on, the current flowing through coil ABCD is going to generate a magnetic field. This magnetic field is going to interact with the magnetic field from the magnet poles. Okay, and the interaction of these two magnetic field is going to cause upward and downward force, and hence the coil turn. I want to see these few key points. I don't want you to just state Fleming's left hand rule. Okay, that's not good enough for me. Okay, part D. Please refer to your book if you are not sure on the function of the split ring commutator. Okay, there's a detailed explanation to it. Okay, go and read about it. Basically, if you look at this commutator here, okay, there is a split here. So what happens is, when this coil start turning, you can see the contact here. Okay, when this coil ABCD start turning, this wire here is going to turn as well, and as it turns, it will go over this gap and then reach the other side. So what happens is that initially AB is receiving incoming current from this side, but as it passes through the vertical plane onto this half of the split ring, the current is no longer going into AB like this side. It's going to be going out of AB. So AB side will suddenly have a change of current direction, and because of that, your coil can continue spinning in one direction. Okay, the book has actually a very detailed explanation on that, so please refer to it. Okay, other than that, you can read the marking scheme stated here. Ways to increase the speed of rotation is quite clear cut also. Moment, sketch the moment versus time. So what you need to take note is that the moment, the upward and downward force acting on the coil is going to be greatest when the coil is sitting flat across the two magnet, because that is the position when the two magnetic field is going to bump into each other most, how to say, violently. No, yeah, there will be the magnetic field from the coil and the magnetic field from the permanent magnet will have the greatest overlap area, okay, when the coil is sitting flat. So that's why you will have the greatest moment here, and as it start turning, okay, there will be less overlap, and so the moment will decrease. Okay, and then what happens? Why does it reach zero? Because remember the split ring, there will be a part when the coil has actually no current flowing into it. That's why you suddenly have the zero moment, because when you have no current, there will be no field, and when there's no field, then there will be no interaction of the two fields, and so there will be no force. When you have no force, then no moment. Okay, then after that it will start building up again and become maximum, and then the cycle continue. Okay. Okay, question 10. This one is like a typical question. Okay, let's see. Part 1. Switch S is closed. Iron core is pulled down and then released. What happened to the galvanometer? So what happened is that when this switch is closed, then the power supply here will give a current flowing into the iron core. So this iron core will now produce a magnetic field. And now when you start oscillating this whole system on a spring, what happens is that the coil in P will experience a change of magnetic field. And according to Faraday's law, when you have a change of magnetic field, you will have an induced current. Okay? And then according to your Lenz's law, because you now need to explain, you need to now explain what you observe in the okay, so this part it does not require you to explain why the galvanometer meter will go up, down, up, down, up, down. Okay, you just need to explain why there's a deflection. So just use your Faraday's law and explain that, because there's a change in magnetic field strength and therefore there will be an induced current, then it should be fine. Okay, in your part 2, so in your part 2 you need to explain your observation in the galvanometer. So whenever you encounter questions like this, first describe what happened, then explain. So first describe, so you have to say that, you will notice that the galvanometer will start having a deflection, and this deflection actually alternates in the same frequency as your spring oscillation. Okay, then after that use your Lenz's law to explain why the deflection, the alternation in the deflection will occur. Okay, but remember to state that the galvanometer is going to deflect at the same frequency as the oscillation in the spring here. Okay, that is a very important point. So just one way to increase this one is your textbook answer. So if you do not understand any of this, come and look for me. Okay. Oh, last question. Last question is your transformer. So again, make use of your transformer equation, plug in the correct value, you should be fine. Part 2, you have to assume that energy is not lost. So when energy is not lost, then power will be the same in both the primary coil and the secondary coil. Okay. Now to draw this voltage time graph, okay, you need to know. Wait, let me see. Is there any tricks? How the voltage vary with time between point A and point B. So point A and point B is here. You already know the voltage is 20 volts. So the only thing you need to work out is what is the frequency. Okay, so the frequency will follow the frequency of the main supply, and you already know the frequency is 50 Hz. So using this 50 Hz, you need to find out what is the period of this graph. Okay, you already know the amplitude is going to change between -20 to 20, +20. The next thing you need to know is what is one wavelength. What is the period here? And you can find out what is the period from the frequency stated here. So since you know that F is 50 Hz, you can deduce that your T is 1/50, and so one wavelength will give you 0.02 seconds. So that's how you determine that, okay, this value will be 0.02. Okay? And whenever you are sketching the graph, it is safer to sketch until you have two wavelengths. Okay, it's just a safety device. Okay, then draw another voltage time, how the voltage across. Okay, this one you have to be careful because they are talking about the lamp. Now if you notice that in your part 3 they are asking you between A and B, and A and B is positioned in front of the diode. So A and B is not affected by the diode, but when you are asked to sketch out the graph for the lamp is actually positioned after the diode, so it's going to be affected by the diode. And if you know the function of the diode, basically the diode will block off all the negative part of the graph. So very simple, you just sketch out the exact same graph, erase the bottom part, and you should be fine. Okay? That's all for paper 2.